This video is on a laboratory technique called photoelectron spectroscopy, abbreviated PES, and I have to give credit to a Mr. Michael Woodward, an AP Chem teacher someplace, for developing the graphs that I use in this video. Now, photoelectron spectroscopy is really an experimental method that determines how tightly electrons are bound to an atom. What this means is that we can use this to confirm electron configuration. The reason is the closer to the nucleus, the tighter the electron is bound to the atom, so more energy is needed to remove it. Why does this happen? Right now, just take my word that the closer to the nucleus, the tighter the electron is bound to the atom. And the nice thing being is we can set this up so the results show up on a graph that is actually quite readable. As you will shortly see, the graph has peaks. The number of peaks on the graph equals the number of orbitals in that element. The highest energy peaks represent electrons in orbitals that are closest to the nucleus. So the graph frequently looks like this, and we'll talk about the x-axis first. And the x-axis is usually labeled ionization energy, or binding energy, or delta U sub E. The units will be in megajoules per mole, or electron volts, and in actuality that doesn't really matter because we're using this descriptively. And the key point here is almost always the x-axis is numbered backwards. We go from the largest value on the left to the smallest value on the right, the opposite of what you're used to doing. And that scale can often be in log form, or you may see double lines on the x-axis that indicates a break or a removal of a section that really doesn't have any data in it. The y-axis is labeled signal intensity, or number of electrons, or the relative number of electrons, and those are the units. And so let me show you what one looks like. This is a photoelectron spectroscopy of an element. Here we have peak intensity and delta U sub E. The highest value is over here to the left at 1,000 megajoules per mole. The lowest value we see here is 0.1, so we're going highest to lowest. And you notice 5 peaks. That means there are 5 orbitals. We can see 3 groupings here. The first grouping, which is the closest to the nucleus because it has the highest energy needed to remove the electrons, is equal to the n equal 1 energy level. The next grouping is the second energy level, and the third grouping is the third energy level. Each grouping is an energy level. That means that these electrons must be in the s orbital. Over in the n equals 2, we have s and p, and for this element, we also have electrons in the s and p orbitals. We see that this peak goes up 2 lines, so there must be 2 electrons in this s orbital, so that's equal to 1s2. This goes up 2 lines, so that has to be 2s2. This goes up 1, 2, 3, 4, 5, 6. So that's 2p6, 1, 2, 3s2, 1, 2, 3, 3p3. So we count the electrons. There are 15 electrons. That means this is phosphorus. This is the photoelectron spectroscopy picture for phosphorus. So I'm going to give you this one here and ask you to determine what the element is. So stop, figure it out, come back, we'll go through it. Go. And the correct answer is magnesium. Here is the first energy level. It has 2 electrons, so that's 1s2. Second grouping, second energy level, 2 electrons, 2s2, 2p6. Over here we have 3s2, so that's 2, 4, 10, 12 electrons. 12 protons, that has to be magnesium. If we continue to go out and further down the periodic table, you would see that this really does follow the mnemonic. This is photoelectron spectroscopy for now. So, to review, PES is an experimental method for determining how tightly electrons are bound to the atom. This confirms, basically, the idea of electron configuration. The closer to the nucleus, the tighter the electron is bound, and I will explain that in the next couple of lectures. And this can all be put into graph form, so it's essential that you be able to interpret the graph. The number of peaks equals the number of orbitals. The relative height of the peaks gives you the number of filled suborbitals, and the peaks will appear in the order of the mnemonic. On the graph, the x-axis usually goes from high to low, the reverse of what we're used to. The y-axis indicates the number of electrons. So when you compare the size of the peaks, they should be a whole number ratio, 3 to 2, 5 to 2, so on and so forth. Think of the intersection of the x and the y-axis as the nucleus of the atom, and therefore each grouping as you move to the right is equal to an energy level. So this makes you guys champions on at least understanding photoelectron spectroscopy. In the next videos, we're going to start tackling periodic trends, and that'll be a multi-video section.